Let's look at the relationship between thermal equilibrium and conservation of energy. Let's consider two objects. They are completely isolated from their surroundings, meaning that as long as they are separated from each other, they will maintain their temperatures. The hot one will stay just as hot and the cold one will stay just as cold. When we bring these two in contact, the heat will flow from the hotter object into the colder object until the two objects reach the same temperature. That is to say, they are in thermal equilibrium. Now, heat is a form of energy, so the heat lost by the hot side is gained by the cold side. So essentially, this is an expression of conservation of energy, that the heat lost from one is equal to the heat gained by the other, or we can write this using signs to consider loss and gain. The heat lost from the hotter object, a negative amount, plus the heat gained by the colder object, a positive amount, is equal to 0. We can summarize this in one simple equation, that the net thermal energy change in the system is 0. That is, if we add the heats, the losses and the gains for a given system, we find that's equal to 0. Let's see how this equation of thermal equilibrium can be used to help us find the final temperature for two objects of different temperatures that have been brought in contact. So in this example, let's look at two equal masses of water at different temperatures. When we mix them together, it's as though we're bringing them in contact. We'll take one to be at 90 degrees Celsius, the other at 10 degrees Celsius. We bring them into contact, and what do we expect to get? Well, we're going to use the sum of the heats equals 0. And we're also going to use our equation that relates heat to mass, specific heat, capacity, and change in temperature, where the change in temperature is the final temperature minus the starting temperature. So let's continue our example. We know that the net heat flow from the system is 0. So we know that the heat lost from the 90 degrees seawater plus the heat gained by the 10 degrees seawater has to be equal to 0. We have our expressions for heat. Heat is given by mass times specific heat times change in temperature. We'll substitute this in for Q for each quantity of water, for the 90 degree water and the 10 degree water. And what we notice is we said that they were of equal mass, so we can eliminate mass from this equation. And they're both water, so their specific heats are the same, and this too can be eliminated. So as a consequence, we have the change in temperature of the 90 degree water plus the change in temperature of the 10 degree water has to be equal to 0. Using our definition of change in temperature being final minus initial, we get TF minus 90 plus TF minus 10 equals 0. Doing a little bit of algebra, we see that we get TF equals 50 degrees Celsius. Not really surprising, it's midway between 10 and 90, which makes sense because we have equal masses of the same substance.